Hello, Bastien. You work for the CEA, which is the French Alternative Energies and Atomic Energy Commission, where you are a research engineer. Could you briefly explain what the CEA is and what you do there?
Hello. So the CEA is a French public research organization. Its mission is to support public policy decisions and to help France and Europe maintain scientific, technological, and industrial leadership. The goal is to contribute to a more secure, controlled, and sustainable future. At CEA List, an institute dedicated to smart digital systems, I work on emerging memory technologies. More specifically, I explore their potential at both the circuit level and the computing architecture level, with a strong focus on hardware, software, co-design.
My work sits at the interface between disciplines. I collaborate closely with materials and process experts at CEA Leti to identify key leverage points at the circuit design level. At the same time, I work with embedded architecture and programming specialists to evaluate system-level capabilities and limitations. During this work, I'll always keep application needs and societal challenges in mind. And that is what makes the research truly exciting.
Well, thank you very much. So today we are going to talk about non-volatile memories, particularly FeRAMs. How would you define non-volatile memories for the uninitiated?
So non-volatile memories, NVM, are used to maintain data without providing supply voltages. They are generally much denser and with higher capacity than fast but volatile memory close to or inside the CPU. Among NVM, we can cite HDD, hard disk drive, and the more expensive but more robust SSD, solid state drive, that has massively replaced the HDD in the PC laptop. SSD and USB key are both NAND flash-based memory technologies. At CEA, we study what we call emerging embedded NVM, eNVM, such as PCM, phase change memory, ReRAM, resistive RAM, or MRAM, magnetic RAM, and more recently, we work on ferroelectric RAM, FeRAM, and FEMFET.
Okay, thank you. So now we are going to go into further details. With what goal is the CEA developing non-volatile memories?
CEA aims to propose and promote differentiating solutions with a view to transferring them to industrial partners.
Okay. In your opinion, what are the most important ongoing projects in this field?
So in terms of ongoing projects, we have industrial collaboration with long-term partners such as Weebit Nano on resistive RAM, STM on PCM, phase change memory, and FMC on ferroelectric-based memory. We have also institutional European and French projects such as FeRAMs and PEPR, Electronics Ferro Futures.
All right. I heard that you were also planning to hold an event which is called Industrial Workshop next year. Could you let us know a little more about it?
Yeah, for sure. On June 22nd, 2026 at Grenoble, just before the Leti Innovation Days, we will be hosting a side event on this topic in the form of a workshop. We have already secured the participation of many key players in the sector, including Ramsid, research centers specialized in ferroelectric technologies, and integrators such as EM Microelectronics.
That looks like a great event. So you focus your research on FeRAM memory, which is a part of the non-volatile memory category. What makes this technology so attractive for research, and what are its specific features compared to other non-volatile memories?
So first, it provides very low write energy, typically at least an order of magnitude lower than what we see in other emerging NVMs. This is extremely attractive in low-power embedded systems. Second, FeRAM offers a very short write latency, usually more than twice as fast as PCM or FeRAM, which make it much easier to use in timing-constrained designs. Third, its endurance is outstanding. We are talking about more than 6 orders of magnitude better than most PCM and FeRAM devices, and even comparable to MRAM, but with a simpler process integration. And finally, FeRAM is naturally robust to radiation, which is a strong differentiator for aerospace, automotive, and any safety critical domain.
Right. How do you envision the use of HCO-based FeRAM in practical applications such as the Internet of Things mobile devices or edge computing?
New process solution of HCO FeRAM will enable FeRAM to jump from 130 nanometer to the advanced technology node of at least 22 nanometer, resulting in significantly higher density and frequency. HCO will thus enable to increase memory capacity previously limited to 8 megabits. Furthermore, using FeRAM instead of MRAM, FeRAM, or even PCM will reduce the energy required for writing by more than 10 times, opening up new markets for IoT or edge computing, where write operation plays a significant role.
Oh, all right. The CEA recently demonstrated 2D and 3D ferroelectric capacitors. Can you tell us about the advantages and trade-offs between these two architectures?
The 2D FeRAM are processed horizontally and thereby easier to fabricate at the cost of a lower density and equivalent capacitance value. A more advanced version called 3D FeRAM is processed vertically in order to enable a much higher density. Thanks to this new process, it's now possible to target very advanced technology nodes, as Micron recently demonstrated in their publication of IEDM 2024 and VLSI Circuit 2025. So the scaling up roadmap for FeRAM looks very promising, and this opens the door to new opportunities, such as co-integration with DRAM on the same chip, something previously considered out of reach.
Oh, that's great news. So finally, I have one last question for you. The miniaturization of FeRAMs opens new doors for sectors that traditionally use this type of memory, as you mentioned. In your opinion, which new players could be affected by the use?
Actually, all industrial players in embedded markets will be impacted by this new paradigm, as FeRAM will significantly reduce the time and energy consumption associated with the data access, facilitating the deployment of AI at the edge. But what's really new today is that even standalone memory players, especially in the field of DRAM, could be strongly affected. They will probably have to rethink how they position and market their products. DRAM can no longer remain just a commodity, as it has been for many years. It needs to become a differentiating memory again, bringing real added value to the system rather than being chosen only for cost and density.
Okay, thank you very much for all your explanations and thank you for your time.
Thank you.